Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. In this video, we're going to finish our deep dive into pygame blending modes. Blending modes specify the color and transparency value of a result pixel when you blit a source pixel to a destination pixel, and they make all kinds of cool effects possible. In the first video, we covered the basics of color representation, creating and blitting surfaces, and how to achieve transparency on a pygame surface. Check out the first video if you'd like a refresher on those topics before we talk about today's blending modes. I'll put a link right here and in the description. In the first and second videos, we covered the default blending mode, the add blending modes, and the subtract blending modes. Now on to our next blending modes, the multiply modes. These are blend MULT, blend RGB MULT, and blend RGBA MULT. As with the other blending modes, blend MULT and blend RGB MULT are the same. In those modes, the alpha channel for the result is the alpha channel from the destination surface. The blend RGBA MULT mode calculates the alpha channel values from the source and destination values. Now, what is this multiplication calculation? This is a scaling calculation. In the blend MULT modes, the source RGB or RGB and A values are normalized, divided by 255, resulting in a factor between 0 and 1. You can think of the factor as a percent. If the factor is 0.75, you can think of that as 75% of the destination color value. That factor is then multiplied by the destination RGB or RGB and A values, giving the result RGB or RGB and A values. So the source red value, for example, is specifying the percentage of the destination red that will be in the result pixel. Note that if the source is completely white, 255, 255, 255, those values divided by 255 will yield a factor of 1, like 100%, and the destination will be unchanged. But any other values will result in factors below 1, which will scale the destination values down, resulting in darker colors. Therefore, with the MULT modes, your result color values will always be the same as or darker than the original. Let's look at an example that highlights the scaling aspect of the multiply modes. This is called multscaling.py. All of the programs in this video are in my GitHub repository for you. There's a link in the description. In this program, I'm blitting an image of a dystopian city to the screen, but before I blit it, I'm blitting a gray surface to the city image using a blend RGB MULT flag. A gray surface blitted to an image using a multiply flag will uniformly darken the image. I've written this program so I can change the lightness of the gray surface by using the up and down arrows, and I have some information being printed over the image so you can see what the current settings are. It also tells me which flag I'm using, blend RGB MULT or blend RGBA MULT. If I press the spacebar, I'll toggle between those two modes. You can see that the starting gray color is 155, 155, 155, 155. And the starting mode is blend RGB MULT. So that 155 alpha is being ignored in this mode. As I press the up arrow and the gray surface gets closer to white, my image brightens. Once I'm compositing white, the result is the same as the original dystopian city image. Now I'll press the down arrow, and you can see the image darkening down to black once I'm at 0, 0, 0, 0. Again, the alpha channel of the source is not being considered. The result is the destination alpha, which is 255. If I press the space bar, now we're blitting in blend RGBA MULT mode. What that is going to do is also scale the alpha channel. Notice when I do that, the window turns red. What I'm doing to make the opacity visible for this example is blitting red to the screen before I blit the image. Right now, with the alpha at 0, completely transparent, we're seeing the red screen. Now, as I press the up arrow again, and we gain color and opacity, we start to see a semi-transparent image over the red background. Until I'm up to an alpha of 255, a fully opaque image, and no red visible. Now, if I want to just scale the alpha, I could blit a surface that is completely white. That will have no impact on the colors of the destination, but with an alpha below 255 to achieve some transparency. A color is on the grayscale if the red, green, and blue color values are all the same. So when I blit a gray surface using a multiply mode, I'm scaling all of the colors equally. What if I blit a surface that isn't gray, that has different values for red, green, and blue using a multiply mode? Then the resulting surface will appear tinged the color that I'm blitting, because the red, green, and blue values will be scaled at a different rate. This program is called slidermult.py. I put a slider on this one because I thought it would be fun to have a way to compare two blending modes. Here I'm comparing the default blending mode on the left with blend RGB MULT on the right. And in this example, I'm blitting a brown surface over the dystopian city image. It is important to note that the brown surface is slightly transparent. It has an alpha of 150. If it were opaque, we would simply see brown in the default blending mode. You can see that the image is tinted brown. In the default blending mode, pixel values are combined according to the alpha values of the source and destination. So each pixel in the original image is a little closer to the brown color of the source. In the multiply blending mode, the alpha is ignored, and each pixel in the original image is scaled to be darker. But the R, G, and B values are scaled according to different percentages. One universal with the multiply modes is that the result will always be the same color if your source is white, or darker if your source is any other color, because each result pixel will be a percentage from 0 to 100 of the destination color, and smaller color values are darker. You can see that the multiply version of this, the one on the right, is darker. It also looks a little crisper because the color values are being scaled rather than mixed with a uniform color, as in the default mode. Now, let's move on to the min and max blending modes. Blend min, blend RGB min, blend RGBA min, blend max, blend RGB max, and blend RGBA max. The way these modes work is straightforward. The minimum color value between the source and destination is used for the result in the min modes, and the maximum color value between the source and destination is used for the max modes. If it's blend RGBA min or blend RGBA max, the same holds true for the alpha channel. Remember that a lower color value will be darker as we approach 000 or black, and a higher color value will be lighter as we approach 255, 255, 255 or white. So how can we use these modes? Max acts as a floor that prevents color values from falling below a certain darkness threshold. Min acts as a ceiling that prevents color values from exceeding a certain brightness. I have another slider example, this time with min and max. For both, I'm using a medium light gray, 150, 150, 150, as the threshold I'm compositing with the min and max modes. With the blend RGB min mode, you can see the darker areas look mostly as they do in the original image, although remember that each component of the color, red, green, and blue, is being compared to the threshold, and so for each pixel, from 0 to 3 of those color components might be replaced by 150, meaning that parts of the image will appear to be a hazy gray as the colors are softened by that gray. In other areas where the colors are bright, such as the center area of the image where we see sky, the gray values are the lower values for all three color values, so the lighter parts are replaced with the gray. With blend RGB max, it is the dark areas that are replaced by the lighter gray, as the gray will have a higher color value than the dark colors, and the lighter values are unchanged as they are higher values than the gray. So the darker areas of the image, like the buildings in front, are replaced with the gray, making them appear either completely gray or hazy gray, and the lightest areas are unchanged. So these modes can even out the brightness values of an image, but replacing the brighter or darker colors depending on which mode you use with a color of your choosing. You can get some cool effects with these modes if you create custom overlays. This short program is called Min Darkness Example, and I'll run it first so you can see what it looks like. The lighter parts of our original image are filled with a blue sort of haze, which radiates in a gradient out from a circle in the sky. My original intention was for that to be moonlight, but I think this actually looks more like some sort of chemical cloud and an opening in the cloud cover, like a low-hanging haze. Maybe that's just the dystopian nature of the original image that makes it seem that way. This image is composed of our usual dystopian city background, composited with a blue gradient overlay I made in Photoshop. It's a deep blue with a gradient to a circular lighter area near the top. When the gradient, the source, is composited with blend RGB min over the dystopian background, the destination, the minimum of each color channel is chosen between a source pixel and a destination pixel. That means the darker color value will win. So where there are light areas in our destination image, they will be replaced with the dark blue color of the source gradient. That's why the middle, where the original image is light, is dark blue, where the gradient is dark blue. Darker color values in the destination image will win over the source blue gradient, so we can still see the darker parts of the image, the buildings, although they are tinged blue because the blue component of the gradient is a lower value than the blue component of the original. And again, Max works the opposite way. The higher values between source and destination will win. This program is called brightness fog example.py, and this is very similar to the slider program, except rather than compositing with gray, I'm compositing with a grayish blue, just to illustrate that you can get a tinged fog effect. The darker parts of the image are blurred and turned bluish gray, and the lighter parts of the image remain the same or are tinged a little bluish. The alpha versions of these two blending modes will floor or ceiling the opacity of the image as well. This example is called min RGBA fadeout.py, and this program first generates an overlay that is all white, but with high opacity at the center and low opacity at the edges. When composited with our background using the blend RGBA min mode, the colors of the image aren't impacted because white is going to be an equal or higher value than the colors in the image. So the white will largely be ignored, but the opacity of the image becomes lower at the edges, giving the image a gradient black edge. And this example is called RGBA max.py. This program creates two spotlight surfaces. These are circles of color that are intense in the center and fade in opacity to the edges. One is blue and the other is orange-yellow. These are then blitted onto a black, fully transparent surface using blend RGBA max. That will choose the highest value for each color value and opacity. Where the two colors overlap, we get pink, because the highest value for each of R, G, and B is being chosen from the blue and orange, and that results in pink. The opacities will be the highest opacity of the spotlight images, so we'll keep the fade. That image is then blitted using the default mode over our city. So the blend RGBA max mode is used to construct an effect that we can blit over our image. The default mode blends the spotlights with our image according to the alpha values in the spotlight and our image, which is fully opaque. Again, this code is in my GitHub repository, so you can download and play with it. Now let's test your knowledge with a quiz. You can pause the video and think about your answer before I reveal the correct answer. On the left is the destination surface created with dest equals pygame.image.load background.jpg.convert alpha. No tricks, it's the same full opacity JPEG from all examples in this video. And in the middle is the source surface created with source equals pygame.surface size pygame.src alpha, and then filled with source.fill 150, 150, 150, so a slightly transparent brown color. And here's my result surface on the right, created with dest.blit source 00, and then a blank. In the result surface, we can see the background image, but it's crisp, darkened, and tinted brown. What goes in the blank? Is it A, nothing, the default blending mode, B, special flags equals pygame.blend RGB MULT, C, special flags equals pygame.blend RGBA max, or D, this cannot be achieved with what we've learned in this video. Pause and work it through. Did you get it? The answer is B, pygame.blend RGB MULT. This mode will scale the destination surface color values by a factor derived from the color values in the source. If the source is any non-white gray, that will darken the destination. But if it is a color, like brown, it will darken and tint the destination. Ready for another? On the left is the destination surface created with dest equals pygame.image.load background.jpg.convert alpha. This is the destination image from the prior question, and again, it's a fully opaque image. In the middle is the source surface created with source equals pygame.surface size pygame.src alpha, and then source.fill 150, 150, 150, 150. On the right, we have the result, in which there is a gray tinge over the entire image, but concentrated primarily over the darker areas, the buildings in front. In the back, we can see the slightly lighter sky. Now we're combining these again with des.blit source 00 blank. What goes in the blank? Is it A, nothing, the default blending mode, B, special flags equals pygame.blend RGB max, C, special flags equals pygame.blend RGB min, or D, this cannot be achieved with what we've learned in this video? Pause and work it through. Did you get it? The answer is B, blend RGB max. Remember, with max, the maximum pixel value is chosen between the source and destination. Larger values are lighter. Max acts as a floor that prevents anything darker than the source surface colors to be blitted, so we get a lighter and blurred out gray image. How about one more? On the left is the destination surface created with dest equals pygame.image.load background.jpg.convert alpha. Yes, it's the same city image. In the middle is the source surface created with source equals pygame.image.load lighterfilter.png.convert alpha. The source is a blue gradient I made in Photoshop. It's a deep blue with a gradient to a circular lighter area near the center top. On the right, we have the result, which looks like a deep purple-blue haze or fog with a circle near the top in which we can see the original image. Now we're combining these again with des.blit source 00 blank. What goes in the blank? Is it A, nothing, the default blending mode, B, special flags equals pygame.blend RGB A max, C, special flags equals pygame.blend RGB min, or D, this cannot be achieved with what we've learned in this video? Pause and work it through. Did you get it? The answer is C, blend RGB min. Remember, with min, the minimum pixel value is chosen between the source and destination. Smaller values are darker. Min acts as a ceiling that prevents anything lighter than the source surface colors to be blitted, so that dark purplish blue is replacing many of the source blues, but in a gradient to the center top where the source has no color, so we can see the destination. This video concludes my 3-video series on the Pygame blending modes. I hope you found the videos fun and informative. Now you can take your new expertise and use the blending modes to full advantage in your games to create custom visual effects. As always, have fun and keep coding.